Lesson 59 is computing area, and we're using the integral to do this. So if you remember, definition of integral is area, and it's area under a curve. And so we've worked with that a little bit, but I don't think very much this year yet. Okay. So we are looking at, given a graph, how do we find the area under the curve? And as you look at this first graphed area, have we talked about how area, if it's above the x-axis, it comes out to be positive? I think we have. And if it's under the x-axis, it comes out to be a negative. So if I'm trying to find the total area of these three shaded sections, I can't just go area 1 plus area 2 plus area 3. Because this area 2 right here is a negative. And so if I just add it, I end up adding a negative, which means I'm subtracting. So our general rule of thumb is we're going to add anything that is above the x-axis and anything that's below the x-axis. You end up having to subtract it, because then you're subtracting a negative, which in turn becomes a positive. And so we're just looking at how to set that up. I think we talked about it a little bit, but I don't know that we've really set it up a lot. Does that sound, am I making a correct comment there? I'm trying to remember what we have and haven't done with integrals. That's where my struggle is at this point. So, questions on that? Seems like it's a little familiar that it's positive above the x-axis, negative below the x-axis. So, as you look at something like example 1, and it says, compute the area, or find the area of the graph y equals sine x and the x-axis between x equals 0 and x equals 2 pi. So, ideally, the easiest thing to do, well, it's the area between y equals sine x and the x-axis. So, x-axis is that baseline, right? So, ideally, we should just be able to do the integral of sine x dx from, what are the boundaries they're giving me? 0 to 2 pi. But this is where we need to look at the graph before we set that all up, because is all of the sine x graph between 0 and 2 pi above the x-axis? And it's not. And so that's where we're going to have to use some of our integral rules we learned last week. So let's look at the graph of sine from 0 to pi. Can you visualize without me having to draw it, or do I have to draw it? I mean, I'm going to draw it, but my point is, do you remember how to draw it? Sine from 0 to pi, or excuse me, 0 to 2 pi. What does sine do?
Up through pi, down into 2 pi.
Starts at 0. Remember, from 0 to 2 pi is a cycle. So it goes up. It maxes above pi over 2. Cuts through pi. There's a minimum below 3 pi over 2. And cuts back up through pi, right? If we're finding the area between the graph of y equals sine x and the x-axis, what area are we finding here? We've got this area on top and this area below, yes? So can I just do the area from 0 to 2 pi of sine x dx? Because essentially that's what they're asking me to do. Find the area underneath the curve sine from 0 to 2 pi. Can I just do this right here? No, because I'll end up the positive, and then I'll end up subtracting what's underneath. So how do I break this up?
0 to pi, sine x dx.
Yeah. So we want to break it up into two pieces. It's still sine x dx in both cases, but using those boundaries. So the idea is that this first one is above the x-axis from 0 to pi. So from 0 to pi of sine x dx. And then my second integral is from pi to 2 pi. pi to 2 pi of sine x dx. Now, am I adding these two integrals? No, because if I add them, I'm adding a positive and negative, and that's not what I want, because this represents a positive value. This is going to be a negative value. So if I add those, they'll essentially cancel out. So we are subtracting them. Questions on the setup? What is the integral of sine? Negative cosine. So negative cosine x, and it's going to be evaluated from 0 to pi, minus, what's the integral of sine again? Negative cosine x, integral from, this time, pi to 2 pi. Remember how to use the fundamental theorem of calculus here? That's officially what it's called, which is why I'm throwing it out there. Fundamental theorem of calculus just says that you plug in pi and then subtract what you get when you plug in 0. So if I write this out, it's negative cosine of pi minus negative cosine of 0. I'll come back and do that here in a moment. And then it's minus the next one, which is negative cosine of 2 pi minus negative cosine of pi. You can use the unit circle to find these values, or what I use is the cosine curve. I use the cosine curve and think about it like that. You can also use the unit circle, which is what I think you guys typically do. What's the cosine at pi? So what's cosine at pi? Negative 1. Now this says the negative of that, so it's going to be 1 minus negative, so I'm going to say plus. What's the cosine of 0? 1. So in that first part, 1 plus 1 is going to be, big math here, 2. Minus the second part. Negative cosine of 2 pi. So cosine of 2 pi is 1. So that's negative 1 then, since there's a negative in front. Minus negative, so I'm going to say plus cosine of pi.
Negative 1.
Right down there at negative 1. Negative 1 plus negative 1? Negative 2. So I now have 2 minus negative 2, which is 4. Officially, it's area. So we can say 4 units squared. So area above the x-axis minus any areas below the x-axis. There's a different way we could have done this. Based on the fact that these are symmetric pieces. Okay, so if we had just done from 0 to 2 pi, it would have ended up 0. Okay, so because if we'd ended up adding these two pieces, a positive and negative would have been negative. Now, but because these are symmetrical, a I don't know if it's a shortcut or not. To me, it seems a little shorter, would be that we could just do 2 of the positive one. So you could have done the integral from 0 to pi sine x dx, and then take that integral and multiply by 2. That is a valid supported option. Because notice, what did we get on the integral from 0 to pi of sine? We got 2. And so it would have just been doubling that and getting it 4. Questions on that one? Okay. Find the area of the region bounded by the graph y equals x squared minus 1 and the x-axis over the interval -2 to 2. So what am I starting with? A graph. Okay, y equals x squared minus 1. What is y equals x squared minus 1? Okay, a parabola moved down 1. And so instead of having the parabola starting at 0, 0, it's a parabola that starts at -1. Now, think about it. My parabola goes through -1, yes? What's a typical parabola shape from the vertex? It goes what?
1, 1, and then square.
Okay, so if it starts at 0, 0, it then goes 1, 1, so over 1 up 1, and then the next point is 2 over 2 up 4. So if I'm doing this without a calculator, not that you could graph on the calculator, but there's some important points to see here. This would be over 1 up 1, over 1 up 1, so we're going to be going through 1 and -1 there. And then also, from the vertex, it would be over 2, 1, 2, 3, 4, and up 4. Which puts us at 2, 3, and -2, 3. Okay. What is the interval I want this area? -2 to 2. So I want to know, I'm just going to kind of -2 to +2. I want to know the area of the region bounded by the graph and the x-axis. So I want to know the area that falls in between the graph and the x-axis. If I'm shading it like I was up above, where am I going to shade? Because that's an important concept to get on this problem. Where are my areas that are between the curve, so like the parabola, and the x-axis?
Inside the parabola. So that'd be -2 to 1, and 1 to 1. They're on the bottom side of the curve for -2 to 1. -1.
Trying to figure out which piece you're talking about, and I got confused.
That little corner there.
Okay. So if we're going between the curve and the x-axis. Right here. Does that fall under the parabola curve and above the x-axis? It does. That's one of the pieces we're looking for. And that's where this one's a little bit more complicated. Like this one up here, between the curve and the x-axis, well, there was this section, there was this section. Here, because we're on that interval from -2 to 2, between the curve and x-axis, well, there is a little portion here. What other portions do I have?
The parallel.
Okay. A symmetric piece over here
Yeah.
that goes from 1 to 2.
And then the dip in between -1 and 1.
Okay, and then do you see the third piece is going to actually be below the x-axis? Which, I mean, come on, think about what we're doing today, right? We're going to have some pieces above, some pieces below. So right there, that's what we're trying to find the area, because we want the area that always falls, if it's above the x-axis, it's going to be below the parabola and above the x-axis. If it's below the x-axis, well, then it's going to end up being above that parabola and below the x-axis. So in both cases, those are the boundaries. X-axis, parabola. X-axis, parabola. Down here, x-axis, parabola. And we know to stop at -2 and 2 because it tells me. Questions on how I did that picture? Okay, so in general, I'm going to write this. We are doing the area of the curve from -2 to 2 of x squared minus 1 dx. Now, can I just do that integral like that? No, because I have how many pieces here? We have 3 pieces here, don't we? 2 of these pieces on top are going to be, these 2 little triangle silvers are going to be positive amounts. What about this piece down here? It's going to be a negative amount, so we're going to end up having to subtract it. Okay, if I read left to right, what's the first integral I'm going to set up?
Could you do that same trick?
Yes.
Okay, I'm going to, can we hold that thought for a moment?
Yeah.
I'm going to write it out the long way, and then yes, we can use that same trick. I'm all for it.
Yeah.
Okay, so if we just break this, I see, can we agree there's 3 pieces of shading? So the first piece is from what? -2, -1. So it's the integral from -2, -1 of x squared minus 1 dx. Then what's the next piece? -1 to 1. Am I adding or subtracting this piece?
Subtract.
Because it's underneath, we're going to subtract the integral from -1 to 1 of x squared minus 1 dx. And then what's my third piece?
Add
From 1 to 2. It's above, so I'm adding it. So I'm adding the integral from 1 to 2 of x squared minus 1 dx. Now that's writing it out the long way. Okay? It was asked over here, and I said, hold on, but I'm ready to talk about now. What do you notice about these 2 triangular slivers? They're the same, right? My picture may not justify them being the same, but it makes sense that they're the same, right? But does it make sense in your head that they're the same? That's what matters. Your picture does not have to be perfect. So, because these 2 are the same, rather than having to do this integral 3 times, plug numbers in 3 times, this is where it would definitely be to our advantage to put those 2 together, and they're the same. Now, here's a neat thing. Which boundaries do you want to use? Do you want to do 2 of the one that is -2, -1, or do you want to do 2 of the one that is 1 to 2? That's That's what I would say. We can do 2 of either of these. Here, if I use the one that is from 1 to 2, that is 2 positives. So before I actually integrate, what I'm going to write this out as is I'm going to say there's going to be 2 times the integral from 1 to 2 of x squared minus 1 dx, and then it's still minus the integral from negative 1 to 1 of x squared minus 1 dx. Now, something like this. I'm going to have us practice doing this by hand. Yes, technically you could plug it into the calculator. But it's not calculator necessity here. This is very doable by hand, and we have to be able to do them by hand just as much as we have to be able to do them on the calculator. So, this 2 right here is just going to stay out front times the integral. Okay, guys, it's Monday. Integral of x squared. What are we doing with integrals and powers? We're going, go up, so you're adding a power and dividing by that new power. So 1/3 x cubed minus the integral of 1 is x. Okay, and that's going to be, in the first case, evaluated from 1 to 2. Minus, well, what do you know about the integral of x squared minus 1?
It's going to be the same.
It's going to be the same. We don't have to integrate it again. So minus 1/3 x cubed minus x, except this time it'll be from negative 1 to 1. Here and here, yes. I don't know which one you're talking about, but, and actually I can zoom in on this now some, that
After this round, will I
I have a little bit of computation kind of written off to the side, so you might, if you have some room to spare for computation purposes. Because if the goal is to not pick up the calculator here, practice those fractions in our head. Okay, so what are we doing? Evaluating from 1 to 2. So remember what you do? You plug in the 2, and then you plug in the 1, and you're subtracting, right? This 2 right here I'm going to keep out front. So I'm plugging in 2. So 1/3 times 2 to the 3rd. What's 2 to the 3rd? 8. 1/3 of 8 is going to be 8/3. Minus, plug in 2, and it's just 2. So that first piece is 8/3 minus 2, minus, now we go back and we plug in 1. 1/3 of 1 cubed is 1/3 minus 1. And then minus. We have to repeat this process with negative 1 to 1. So now, plug in 1 at first, the upper boundary. 1/3 of 1 cubed, so 1/3 minus 1. And then minus. I'm going to plug in the second number, which is negative 1. So 1/3 of negative 1 cubed. Negative 1 cubed is negative 1, so negative 1/3 minus x, and it's minus negative 1, so that's really going to be plus 1. Can you clean that up without a calculator? You're supposed to be able to, right? I'm going to keep my 2 out front here. Okay, if we just look in this first area here, the 8/3 minus the 2 minus the quantity 1/3 minus 1. How much of that can you guys do in your heads?
2/3 minus 3rd plus 2/3. So 4/3.
Okay.
Not counting the 2.
Right. Okay. I agree with 4/3 for the value from bracket to bracket here. Okay. He totally did it differently than what I was going to do, but that's fine. We all do this different in our own heads, right? So he said 8/3 minus 2, so that'd be 8/3 minus 6/3 is 2/3. Over here, 1/3 minus 1 is negative 2/3. 2/3 minus negative 2/3 becomes 4/3. So I now have 2 times 4/3 minus, we do something similar over here. 1/3 minus 1 is negative 2/3 minus negative 1/3 plus 1 is positive 2/3. So we've got negative 2/3 minus 2/3, which is going to be negative 4/3. Two times, if we go back to the beginning here, 2 times 4/3 is going to be 8/3 minus negative, so really it's plus 4/3. 8/3 and 4/3 is 12/3, which is 4. 4 square units.
Units squared.
Yes. Not that you can, yeah, I forgot the square, sorry.
I didn't know if I was supposed to write it or
No, you should. Now, in all honesty, calc test, I'm not sure they really expect labels on that type of stuff. So it's not a huge, I don't think. Okay, example 3. I think I get moving. I feel like this is not too horrible, but I feel like I'm dragging it out. I'm going too slow, maybe? I don't know. Okay, moving along. Find the area of the region completely enclosed by the graph y equals negative x cubed minus x squared plus 2x and the x-axis. Thoughts?
I always draw it using graphic calculator.
Well, do you know what the graph of negative x cubed minus x squared plus 2x looks like?
no, but I calculated.
Well, it's negative x times 20x plus 2 times 20x minus 1.
Okay, can you graph that by hand?
Mostly.
Okay, so I'm going with we don't know enough about this one to graph it enough by hand. I mean, we could come up with some details. Wait. I mean, there's some details we could get. It's x cubed, so we know in the behavior it starts with a negative, so that can help us with where it starts. But we're also going to have to know exactly where it's crossing the x-axis, which actually is doable to find here because it would factor. Yeah, it would factor. But I'm also okay with graphing this one by hand, or graphing this one with calculator. Negative x cubed minus x squared. Actually, I guess if we did factor it, we could graph it enough, but it's fine. Okay. Got a graph like that? So what do you notice?
It's negative from negative 2 to 0.
Okay.
From 0 to 1.
Okay. Looks like it crosses the x-axis here at negative 2, 0, and 1. At negative 2 and between negative 2 and 0, there's an area below the x-axis. Between 0 and 1, there's an area above the x-axis. So because I like to have a picture to point at and draw on, I'm going to sketch the picture. Okay, there's my basic sketch. Goes through 0, goes through 1, it goes through negative 2. So if we're trying to find the region between the graph and the x-axis, we've got a section over here and a section over here. The section on the left is below the x-axis and thus negative. The section on the right is above the x-axis and positive. Now, I tend to start off writing it like this, in the idea that I'm doing the integral from -2 to 1, because it says find the area of the region completely enclosed by the graph and the x-axis. They didn't tell me the boundaries, I guess. And did you guys catch where the boundaries came from? Okay, tell me if not, but it's just because that's where the end points it crosses the x-axis. So I was able to break it into the two sections. As I set this up, what's my first integral going to be?
Put a negative in front.
Uh-huh.
And then have the -2 to 0.
Okay, so if we use going left to right, the x values are -2 to 0. And notice, why did he say put a negative in front? Because it's negative, right? We have to counteract for that negative. And it's going to be of -x³ minus x² plus 2x dx. And then, what about the next integral?
And the 0 on the
Okay, it's a positive amount because it's above, so we're going to add, and it goes from 0 to 1. So we are adding the integral from 0 to 1 of -x³ minus x² plus 2x dx. If that bugs you having the negative integral out front, could you have flip-flopped these? Sure. If that just, I went from left to right, I'm fine with that. But I get it. If that negative bugs you, if you're afraid you're going to forget it, then by all means, feel free to make this turn around, make it a subtraction problem. Okay. Excuse me. So this first one is going to be the negative of, let's integrate, integral of -x to the third.
-1/4 x to the 4th.
Okay. -1/4 x to the 4th. Add 1 and divide by that 1. Minus the integral of x². X to the third over 3. Also 1/3 x³. I'm fine with either way. Integral of 2x. Okay, you add 1 to the power, it's x². You divide that, so it just becomes x². First time it's going to be evaluated from -2 to 0. And then plus, you don't have to integrate again, but next time it's going to be evaluated. Did anyone catch I didn't write that 4 up there? We said it, so.
Where?
On my x to the -1/4 x to the 4th. I just hadn't written it. So -1/4 x to the 4th minus 1/3 x³ plus x², and this time it's from 0 to 1. Okay. I'm going to keep my negative out front. I'm going to set up brackets for the whole thing. I tend to do first part in parentheses, second part in parentheses. So, what am I plugging in first?
You don't need to plug in 0 because that's all
Okay, now, and I agree to an extent. However, be careful about you don't need to plug it in.
Yeah.
You're still plugging it in, but it's going to result in a 0, right? Because you're going to have 0 to the 4th minus 0 to the 3rd plus 0 to the 2nd. So I agree it's all going to be 0. Yes, I get it. Don't just totally forget it, because what are we doing with the next part? We are subtracting. So what you've really got to think is this is going to be 0 minus whatever I have right here. Mistakes I see. Now I'm plugging in -2. So negative 2 to the fourth. 2 to the fourth is 16. Divided by negative 4 is negative 4. Negative 2 to the third is negative 8 times negative 1/3 plus 8/3. And then plugging in negative 2 to x squared. Negative 2 squared is going to be plus 4. I'm ending the parentheses. I'm ending the bracket. Now repeating the process the next time. Now it's a big old plus. And what do we plug in first this time? The 1. So negative 1/4 x to the fourth is going to be negative a fourth minus 1/3 x cubed minus a third plus x squared plus 1. That's the first part minus the second part. What am I plugging in next time? 0. And so, I mean, you could just write one big 0 there. Just always stop and think, because if something doesn't have an x on it, that 0 matters, right? Okay. Well, let's see. In these parentheses right here. I like this first one. You guys realizing what's happening? Negative 4 plus 4. Cancel, so I have 8/3. It was minus it, but it was also negative, so all over that is a positive 8/3. You guys okay with that? If only the next one was this easy. Not that it's horrible, but okay. Fourths and thirds need a common denominator of 12. 1/4 is 3/12. 1/3 is 4/12. Negative 3/12 minus 4/12. Negative 7/12. But then we're adding 1, which is 12/12. Negative 7/12 plus 12/12 is 5/12. Minus all those zeros. Now, the common denominators aren't working in your head. Write it out, yes? 8/3 plus 5/12. This needs to be 12, so multiply by 4. 32/12 plus 5/12 makes it 37/12. 37/12 units squared. Okay, so that one technically could have been graphed by hand. Could have all been done without the calculator. We graphed it on the calculator though. We've got one more to look at. We better. We should. Here's the thing. Well, we should. I'll just leave it at that. I don't want to give away too much of the problem. Notice what it says. Very first sentence there. Calculator. Which is why we should be able to make it through. We don't have to do all the integration by hand. We can use the calculator to find areas on the graphing calculator. Simply be careful of graphs that lie both above and below the x-axis. Okay, so the catch is going to be, this one's not nice numbers. So, let's graph it. X to the third minus 7x squared plus 2x plus 5. Okay, you got a visual? I'll be honest, officially I can't see on my graph, but do you have an idea of what it's doing? I mean, honestly, you know enough there. Because what's happening? My graph starts low, right? It starts low, cuts up through the x-axis and the negative, cuts up, crosses over the y-axis, comes back down, goes way down. We don't know how far. I don't care. And then comes back up, right? Is that the gist of what's happening? And that's enough to know us, to know what we're doing. What are we trying to do here?
We need to find the zeros first.
Okay. We've got, how many areas are we going to have here? We've got 2 areas, right? We've got an area above the x-axis and we've got an area below the x-axis. Jack said something about finding the zeros. Do I know where my graph crosses the x-axis? Does it look like it crosses the x-axis at whole numbers? No. This is a required calculator usage because we're going to be working with decimals. And so that means we're also integrating on the calculator. So, you guys are pros at finding zeros, right? Second calc 0, left bound, right bound, guess. And so this first one, negative 0.6868. Okay. Redo, second calc 0, left bound, right bound, should be 1 point something. 1.1062. And then repeat the process one more time. There it goes. Your left bound or right bound, 6.5806. So that's all your calculator doing the work. Okay. And what do we know? The area above the x-axis is positive. The one below is negative. What's the first integral I set up? What are my boundaries? Okay, so if we're doing the positive section, it's a boundary of negative 0.6868 to the boundary 1.1062. And that's going to be of the integral x to the third minus 7x squared plus 2x plus 5 dx. And then what's my second integral? It's going to be a negative, so we're going to have to subtract it to counteract that. The integral from the 1 number to the 6 number, right? 1.1062 to 6.5806 of x cubed minus 7x squared plus 2x plus 5 dx. What, zoom it in? Well, ask. I can usually zoom in some. Okay. So, I don't know about you guys, but I'm not touching that integration by hand. I mean, I could integrate it by hand, but then I still have to plug those numbers in, which requires calculator usage, right? So you guys remember how to use your calculator to do this? Okay. I was going to say math 9. He said alpha something. I don't know what that's. Whoops. Yeah. It's in there somewhere. I know that. So, math 9 or your alpha shortcut. So, negative 0.6868 to 1.1062. X to the third minus 7x squared plus 2x plus 5 dx. Now, you have options. Do you want to hit equals and find that value? Or do you want to go ahead and type in your second integral also? Okay. With these calculators, it honestly doesn't really matter, does it? If you find them individually, you can then go grab the values, like highlight them and grab them, so it's not like you have to retype them or anything. But I'm fine with just then minus another math 9, and then going from there, 1.1062 to whoops, try this again. It's 0.5806, and then type it in. 7x squared plus 2x plus 5 dx. And if you've typed it all right, no mistakes typing, you should get this answer. Sorry. Yeah, if you're still typing, by all means, keep typing. But that's your final answer, is what I'm saying there. So, 129.995 units squared. As much as I want to round that up and say 130, I'm not going to because AP Calculus wants 3 decimal places. Okay, so what I will say is if you didn't get that answer, I can help you figure out where you typed wrong. Or if you're just not there yet, keep trying it, guys. Okay, so you probably have honestly a typo in there somewhere.